Hello and welcome to today's webinar presentation of the LandScan and LandCast datasets, which is part of an Oak Ridge National Lab licensing opportunity announcement. I'm David Sims, a commercialization manager here at ORNL, and today the overview of LandScan will be presented by Amy Rose, who's the leader of the Population, Distribution, and Dynamics team within ORNL's Geographic Information Science and Technology group, and the overview of LandCast will be presented by Jacob McKee, who's a researcher on the Population, Distribution, and Dynamics team. So if you would, please hold any questions until after Jacob's LandCast presentation. So I'll turn this over to Amy now.
Good morning, everybody. Oops, I've already messed up the slides. All right, so I just wanted to give a quick overview of what we've been doing at Oak Ridge for the past several decades, really. We've been engaged in developing population distribution algorithms since the 1970s, certainly for site assessments, certainly for this particular site at Oak Ridge National Lab, but also other areas to improve the resolution and fidelity of spatial population distributions. And so for the last 20 years or so, we've been producing LandScan Global, which is what we consider our flagship product. And so today I'm going to go over some of a high-level description of what that data set is and how it's developed. And then Jake is going to talk about a newer development, which is LandCast, which is spatial distribution projections for the US. So what is LandScan? LandScan is essentially improving the knowledge of where people are located. So LandScan is a population distribution model, it's a database, it's a tool. And what it is it's developed from census and other spatial data using a regular uniform grid. And so what I mean by that is in order to get away from having non-equal areas, what we do is apply all our algorithms to a 30 arc-second grid. So the reason that LandScan Global was first conceived was to develop a more realistic population distribution for consequence assessment. So what we would consider basically an unwarned population. And the reason for this is that any type of event, whether it's conflict, natural disaster, any kind of emergency or evacuation, could happen at any time during the day. And so what we wanted to do is do better than just a residential population distribution, or what you would consider kind of a nighttime distribution. So while we still use census information, we want to also incorporate kind of the full activity space of where people are during the course of the day. And so LandScan Global is what we call an ambient population. So the distribution of population is averaged over 24 hours. So you'll see people and the population counts in places where you would expect. So, larger cities, urban areas, fewer people in rural areas, but all while taking into account local and regional variations in what those cultural practices are. So LandScan is a spatial resolution of 30 arc seconds, so it's about 1 kilometer at the equator. And we use a lot of remote sensing-based data for modeling and mapping LandScan Global. We perform annual updates on LandScan Global, so incorporating new census information, including mid-year population estimates, also new administrative boundaries at subnational level, and of course always exploit any new spatial data and imagery which comes online during the course of a year. So every single country is updated annually, whether it's a small improvement based on available data or large changes. There's a variety of applications that LandScan's been used for currently and in the past. Certainly, as I mentioned before, any kind of emergency response, humanitarian response, consequence assessment. So a variety of systems already use this as their population of record, so things like pagers, so the prompt assessment of global earthquakes. So we've been called on to supply this information for a variety of natural disasters, tsunami, the earthquake in Haiti and in Pakistan, and a variety of other both government and humanitarian organizations have used this information to do pre- and post-assessments of events. So I mentioned that LandScan Global is enhanced annually. Now, the 30 arc-second resolution has been the resolution since the inception over 2 decades ago. But the improvements actually improve the spatial fidelity. So while the 30 arc-second resolution is what we always produce, you can see over the course of each year that we go through, new spatial data information, new modeling techniques allow us to improve that spatial fidelity, to really improve where the likelihood of people being located is. So these annual refinements are based on, as I mentioned, new country censuses, and that can include microcensus surveys, that can include full census, that can include population registries, any kind of population enumeration that we can discover for a particular country or subnationally. New administrative boundaries, which are critical and always changing. Any ancillary infrastructure data, including roads, points of interest, buildings, anything like that. And certainly accounts of IDP and refugee movements. For the past several years in LandScan Global, we've actually, for Syria and the surrounding countries, actually used the most current situation available to report those numbers. And so while typically the timestamp for, let's say, LandScan 2016 is July of 2016, what we're actually doing for Syria and the surrounding region is for this year, when we produce LandScan 2016, Syria and the surrounding region will actually be May of 2017. So that's really just to account for the dynamic movement of population that's going on in that area, and to make it a more realistic answer for certainly the uses that we see in LandScan. And then we also include input from our settlement mapping and LandScan HD. So settlement mapping is basically using machine learning, computer vision to exploit high-resolution imagery and extract settlements very rapidly at a very high resolution. So using those settlement extractions to understand kind of the baseline of where people are located. And then LandScan HD is another product that we develop at a 3 arc-second resolution for some areas. And what we do is where we have LandScan HD developed, we'll incorporate that to improve the spatial fidelity of LandScan Global. So the LandScan framework is kind of 3 parts. So obviously it includes spatial data associations, whether it's raster, vector, or other types of data. So for raster data, we of course include things like land cover, elevation, slope, to kind of understand the likelihood of where people are. Certain land cover will have higher likelihood of having people there. Certain elevations will exclude population from settling there. Certain slopes, same case. And so we don't do just a global model for all these different types of features. What we do is we take into account what are the differences locally and regionally that may preclude somebody from being in an area. So in some parts of the world, people don't really build on steep slopes. Other parts of the world, you have large amounts of people building on steep slopes. So we take those factors into account. Then, of course, vector data such as lines and polygons, roads, rail, waterway, any kind of infrastructure that also indicates a higher likelihood of population being located there. And then points, whether it's towns, villages, building data. And then this would also include now some of the settlement mapping data that I've been discussing. Cultural data. So what are the characteristics of those settlements? So even though we might understand the built environment and how that might indicate a higher likelihood of population, it still doesn't give us really the differentiation between densities of population. And so we incorporate cultural data like urban densities, so how compact the buildings are, urban Z dimension, so obviously if you have tall buildings, you're probably going to have more people there. Rural densities and settlement types, so understanding the differences between nuclear, linear, dispersed settlements, and then incorporating economic factors and agricultural intensity. Agricultural intensity is a key piece of information here because, as with other types of things across the world, agriculture is practiced a little bit differently in some places than others. So, in the U.S., you would not necessarily see too many people out in fields during the course of a day because it's highly mechanized. Whereas other parts of the world, you would see more people in agricultural areas. So our methodology basically starts with inclusions and exclusions. So inclusions being, of course, developed areas, places that we know people will be, And then exclusions, so permanent ice, extreme elevations and slope, and water. And while some people do live on houseboats and in water, for this particular product, we do exclude people living on water. And then we use all that information about inclusions and exclusions to develop a likelihood. So combining spatial data and cultural settlement characteristics into basically a weight or likelihood of how likely it is that people will be living in a particular cell, working in a particular cell, having some type of activity in a particular area. And then the high resolution imagery analysis we use both for the development of the model, but also for corrections and modifications. So going back and looking at really what's on the ground in order to determine whether the census information is as we expect. There's a lot of times when we have census information that might be outdated, or where there's large amount of growth in a certain area. So what we like to do is make sure that those numbers are actually keeping up with what is going on the ground. So how's LandScan developed? It's basically a smart interpolation spatial model. So as I mentioned before, we're taking all these pieces of information from population data to the spatial data associations and creating a likelihood model. So this particular example is just strictly looking at using land cover. So for example, if we have high density residential, low density residential, evergreen, and forest, we would weight these differently based on how people inhabit those areas. And so you can see the grid at the bottom left where we've weighted these particular factors. And these weights will change depending on region, certainly. And then what we do is we aggregate those coefficients and then take the amount of population that's reported for that area and using those coefficients, distribute that population. We do make adjustments after the fact, as I've mentioned, based on any additional information we have about an area. Certainly, this is really simplified, particularly for areas like Syria that's experiencing a lot of dynamic movement. So there is additional validation verification steps that go on after this. But this is the general model, basically building likelihood weights for the entire globe and then distributing population counts to those weights. So one of the things that is really important, particularly for mapping population, is being able to capture new development. New development is cropping up everywhere, whether it's Las Vegas, whether it's Middle East, not just newly developed existing land, but also new land is being created. So one of the things that we've developed more recently here at Oak Ridge and been working on for the past few years is, as I mentioned, some of the machine learning and computer vision algorithms to rapidly extract settlement features from high resolution imagery. So kind of the way that had been done historically is you use a sensor information, something like maybe a Landsat, which is temporally pretty coarse. You don't have it, or previously didn't have it flown very recently, and then also spatially in some sense pretty coarse also. And the picture on the left, you see kind of what urban would be according to Landsat, and how big swaths of areas like in the green are missed. And so what we want to be able to do is do better than that. So one way people have done this in the past is hand digitize that. So that obviously gets you a better answer, but if you can imagine, that's really not scalable for the entire world. So we want to move beyond having to hand digitize areas and really get to a point where we can use the feature information that's in imagery to automatically extract those settlement characteristics. So what we've been doing is now scaling this to the world. So both mapping settlements as well as mapping building areas to basically give us that foundational data layer to map population for the world. So obviously this is a big step between just the mapping of the settlements or the buildings to population. But this is a great first step, and it gets us past the point of relying on other foundational data to do that job. And so with that, I'll turn it over to Jake to talk about LandCast.
So LandCast is basically some tangential research that really kind of spawned from LandScan and LandScan Global. But really, instead of looking at the current population distribution, LandCast actually projects that population distribution into the future. So it's a projected distribution of gridded population for the contiguous U.S. Originally, this was developed for the Department of Energy, for the Department of Energy being able to meet the future energy demand and where to site future energy infrastructure to meet that demand of growing population. One reason we actually developed our own method as opposed to using any of the other generic modeling scenarios is that the existing modeling scenarios really apply these coarse or generic trends to broad regions of the globe. Specifically, you may have one particular growth scenario for all of North America, when we in fact know that there are spatial disparities in growth patterns at really small scales. So while we originally developed this for this locally adaptive framework for siting energy infrastructure, it has numerous applications, including those that you see here, such as urban resiliency, sustainable infrastructure, as well as assessing impacts of climate change. But the real thing that sets LandCast apart from other population projection modeling frameworks is this locally adaptive nature. We modeled every county differently because we knew that while everybody knows and most demographers know that you have different growth patterns, population growth patterns for each county, but you also have varying spatial growth patterns. Not all that population is going to become sprawl. You're going to have different patterns of infill where people go to inhabit current existing urban areas, while you're going to have some population that's going to become sprawl. So while LandScan looks at current infrastructure and current data layers to model existing population, LandCast actually looks at the past roughly 30 years of spatial population growth patterns and models that going forward. And so just evidence of that is we looked at the past 30 years of historical land cover change and what areas developed, what land cover classes developed into urban, and we then quantified that at the county level. So you can see here, this is for the past 30 years. This demonstrates the dominant land cover class that was converted to urban for each individual county. And even at the regional level, if you think about the southeastern U.S., the northwest, the northeast, even within those broad regions, you still have spatial disparity in the land valuation and what land cover types are valued and are not developed. So this kind of was the springboard for modeling and the development of the LandCast framework. So this is just an example of the modeling framework that was used for Scottsdale, Arizona. Again, everything was held constant at the county level, so all the weights, the modeling techniques, the input data sets were all tailored to the individual county level, which brings up the locally adapted nature of this. So we looked at the current distribution. So we took LandScan as our baseline data. And we said, all right, projecting the future, how is this going to change? And we started by looking at the past 30 years of land cover change, which is this historical development slide here. We looked at what areas were most likely developed or most commonly developed into urban areas. We then incorporated some varying population gravity model aspects, which is based on the assumption that population attracts future population and attracts more population. And a lot of times population helps to quantify certain intangible aspects which may not be captured in other data sets. You may not have complete coverage of infrastructure data, but that population may represent something that is intangible and difficult to quantify. So, which is why you rely on the population modeling aspect, population gravity modeling aspect. We looked at distance to roadways, but we also incorporated the National Household Travel Survey to look at people's population's willingness to commute, and that varies, especially if you live beside a large urban city, a large sprawling urban area. You don't tend to travel as far because you are close to certain amenities. Even if there is something further out, you may stick to the one that is closer just because of convenience. So incorporated that and people's willingness to commute to certain amenities. And then once we had all that data, we then merged it all together to create this potential development surface. So looking at the future, the bright areas in this case are more likely to become developed. Again, more likely to become developed is still dependent on the amount of population growth that is going to occur, which is two separate details of this modeling, the spatial aspect versus the population aspect. So this is not to say all these areas in red here are going to become developed, but if population growth was likely, this is most likely where that growth would occur. Once we had actually projected the actual population growth for that area, we then distributed that population to the potential development surface, giving us our projected distribution for the years 2030 and 2050. So looking at the aggregate level of the contiguous U.S., this is actually just a graphic showing the projected change from 2010 to 2050, where the bright reds show population growth, while these spikes show population growth along with the development of new urban areas. So in places like Atlanta and things, and New York, where you may still be having population growth, there's already urban areas. There are already the infrastructure exists to support that population. In other areas where you have these extrusions, these spikes, it's saying that there's going to be more people. There's also going to be associated growth in the amount of urban area for those regions. But for the LandCast data set, it's for the years 2030 and 2050, and it's at again, as Amy mentioned, it's sticking with the LandScan. It's an ambient distribution, so it's basically a 24-hour average, and then again, it's at the 1 kilometer resolution.
So what's included with both of these products under this licensing agreement? For LandScan Global and LandCast, both are delivered in Esri grid format, 30 arc-second resolution for both of those. For LandScan Global, of course, it's global coverage. For LandCast, we have the continental United States. As far as temporal availability, LandScan Global, this would be for the year 2016, and then 2017 and 2018 would be based on availability. For LandCast, it's, as Jake mentioned, years 2030 and 2050. And then this data will also include an ArcGIS layer file with legend classification, so it's easy to import. And also for LandScan Global, we do have historical data sets available ranging from the year 2000 to 2015.
Appreciate you joining the webinar today, and thank you, Amy and Jake, for the presentation. And if you've got any questions, I'm David Sims, a commercialization manager here at ORNL, and the email address is sims, SIMSDL @ornl.gov. Thank you.